All right, should be 32 in the first box and 19 in the second box. I'm sorry, guys. Sorry. All right. So taking it out to 2 decimal places, that means our p hat value is 0.59. 0.59. All right, let me see. There we go. Perfect. So we're going to do the state part together. And we're going to do part of the plan part together. So we've already practiced writing our parameter. Since we're finding a proportion and our statistic is p hat, what would the parameter be? Which symbol would we use for parameter? P. So I would have P equals. And what were we trying to estimate? Proportion of earth covered by water. So this would be the true proportion of earth covered by water. Confidence level. What's the most common one that we've done so far? 95. Up here they ask us to do a 95% confidence interval. And I'm going to go ahead and just write this down right now. If we're doing a 95% confidence interval, what will our critical value be? $1.96. For a 95% confidence interval, the critical value would be 1.96. All right. Let me pop that up a little higher on the screen. Oh, good grief. Sorry, let me fit this stuff in where it needs to go. All right. That is the state step of the 4-step process. You name your parameter, and you state what the confidence level is. So what is it that we are trying to find or trying to estimate? And what is the confidence level that we're going to use? So 2 things in state. Plan. 2 things in plan. We're going to have the name of our procedure here. The name of our procedure that we're going to use today is a 1 sample. Because we only did this exercise 1 time. We threw the ball around the room. You guys came up with 19 waters out of 32 total ball tosses. If we did it again today, then we would have 2 samples, but right now we just have the 1 sample. This is a 1 sample Z interval for, what's our parameter again? Not all the words, but what's the symbol we're using? P. This is a 1 sample Z interval for P. For this whole chapter, it's either going to be a 1 sample or a 2 sample Z interval for either P or P1 minus P2. If we have 2 samples, we'll do P1 minus P2. If we have just 1 sample, we're going to do a Z interval for P. Checking conditions. What are the conditions that we need to check here? Random. What else do we need to check? Independence. How do we check independence? 10% condition. So we check random, we check independence, which is 10%, and what else do we need to check? Large counts. What are we checking for when we do large counts? Normality. I want you guys to go ahead and check those conditions. Check our conditions. We did a random sample of 32 locations, so we absolutely get randomness. I don't know what could be much more random than throwing the ball around the room. Do we get independence? 32 is less than or equal to 0.10 of all locations on Earth? Yes. Do we get large counts? Yeah, what is 32 times 0.59? 18.88, greater than or equal to 10, so we're good there. And 32 times 0.41, you said 14.12? 13.12, thank you. That is greater than or equal to 10, so we get that. Why is randomness important? There we go. We want an unbiased sample, but the reason it has to be random is so that we can generalize the population. %% condition. I know we're going after independence here, but why are we meeting this 10% condition? How does that show independence?
There's like enough of the population that taking one out in a sample is pretty insignificant.
Yes, absolutely. The way we're going to write that shorter is that sampling without replacement is okay. And we already kind of stated why we're doing large counts. We're checking for normality, because what's that going to allow us to do? Yeah, we're going to be able to use a normal CDF. So this tells me that the sampling distribution of p hat is approximately normal. It's going to let us use normal CDF. All right, general formula for any confidence interval. We're going to write this out in words. The general formula is words here. That is our point estimate plus or minus the margin of error. What do we use to represent the point estimate? P hat. So we have P hat plus or minus. How do we calculate margin of error? Yep. Z star. Standard deviation formula, but with one key difference. P hat instead of P. So P hat times 1 minus P hat over n.
What's the star mean?
What does the star mean? It means it's a critical value, and the z is for the normal distribution. So we have a critical value for the normal distribution. That's what z star together means. I want you guys to plug your numbers in there. Everybody should have the exact same, so if you want to work with somebody, that's fine. But we all have the same p hat because we just got one sample as a class. And everybody's margin of error should be the same. So take about 2 minutes and calculate our confidence interval. Absolutely, you can. You're welcome. 0.17 for our margin of error. 1.96 times the square root of 0.59 times 0.41 over 32. So you should have gotten 0.17 for your margin of error, which means our interval would be what? 0.42 to 0.76. We've just done 3 steps of the 4-step process. State, where you name your parameter and you name your confidence level. Plan, where you say what testing procedure you're going to use and you check your conditions to make sure you're allowed to use all the formulas and all that jazz. Then you actually do it. You plug the stuff in. You find your margin of error. You have your point estimate. You find your interval. And then conclude. We have practiced doing this already. How would you interpret that confidence interval? Absolutely. We are 95% confident that the interval from 0.42 to 0.76 captures the true proportion We're basically just going to restate what we said P was here. Captures the true proportion of Earth that is covered by water. Beautiful. That is the four-step process. State, plan, do, conclude is our four-step process. State, parameter, confidence level. Plan, what procedure are you going to use? Are you allowed to use all the pieces? You checked your conditions. Do, pick out which formula you're going to use. Plug in the pieces for the formula. So far, this is the only formula that we have. And then conclude, interpret it in context. Curious, how good do you think we did? Do you think that that interval captures the true proportion of Earth that's covered by water? Do you think it's somewhere between 42 and 76%?
Yes.
Does anybody happen to know what it's about?
About 77%.
It's about 71%. We captured that in our confidence interval. Nice job. All right, let's flip it over. So four-step process. You guys have that page that goes along with your homework. If you can fit state, plan, do, conclude into the little space that's on your homework, if you like to write small, you are welcome to do it on the homework page. If you need some more room because you're having to do your work and you're having to explain, use that other sheet that you guys picked up on your way in on Wednesday. If you need another copy of it, I've got more copies. I'm happy to pass them out. It's got four-step process on either side. So you can do both of the problems where you have to do your 4-step process. Choosing a sample size. This is something that we have not practiced, and we're going to practice this on the check your understanding part here in just a second. What happens when we increase our sample size? What'd you say? Our interval is going to get narrower. We can keep the same confidence level and make our interval narrower by increasing our sample size. So sometimes we start off with, I want my margin of error to be no more than 1%, so 0.01 on either side. How big of a sample size would I need in order to be able to guarantee at a 95% confidence interval my margin of error is no more than 1%? The way we do this, you're going to use your formula for margin of error. This is what we add and subtract to p hat. We're going to solve it for n. We know what we want our margin of error to be, so we can plug something in there. We know what we want our confidence level to be, so we can put our critical value in here. When p hat is unknown, maybe I haven't even taken my sample yet, so I have no idea what p hat is. We're going to use a conservative estimate. We're going to use 0.5. When I multiply 0.5 times 0.5, that's the largest that numerator could possibly get. And then we leave n just n. And we're going to solve that then for n. Do not round in the middle of the problem. You're going to divide your margin of error by your z star, by your critical value. Then you need to square both sides. And then you're going to multiply by n and divide by what's on the other side so that you isolate n. If n has a decimal, say you found out that you need 37.5 people, 37.1 people, we're always going to round up. Remember, we want that margin of error to be no more than, so more people is better than less people. I need to find out the minimum number of people, so if it's point anything, round up. So far, so good? Let's give that part a try. Let's check our understanding down here. Yes, you can. So I want you guys to try to practice solving for n on number 1 in the check your understanding. No, you're fine. I almost didn't hear you call my name.
I think I'm a little bit confused here. I get this, the p hat, but
You forgot your star there. It has to have that little asterisk.
I think the only thing that gets me confused is the margin of error.
Let me go grab. Right. Yes, those. Here's how you can find it if you don't know what it is. Norm 1 minus the percent, the confidence percent you want, over 2. It's going to give you a negative number back when you do that. The critical values are never negative. Just ignore the negative part. That's Z star. And then you have called the standard error. That is this part. Margin of error. Z star.
Margin of error is z. Z is always going to be the interval of this, right?
Z star is that critical value. This right here is this.
So z star is critical value.
Z star is critical value. They chose Z star to mean critical value is beyond G, but that's what they picked. I kind of understand the Z part because it's coming from inverse norm, and Z gets used for normal stuff. But Y star, so the Z star we have to 1.96, and then we plug in our T hat. 1 minus that to be 0.41 over 32. And so then I took this whole thing right here and typed it into my calculator, and that's where the 0.17 came from. Yep. Minus it to get the bottom, add it to get the top.
The first number is always going to be the lowest.
Yes. Awesome.
I think I was just getting myself confused with this right here.
Yeah.
Is that different?
Yes. Yes, it is.
Thank you.
You're welcome.
Can I keep this?
All right. Does anybody have a number of people? You need a minimum sample of what? Right. I heard like 3 answers. All right, so our margin of error is equal to Z star times the square root of P hat times 1 minus P hat over N. Margin of error, we want to be at most what? 2%. So how would I write that in decimal form? Yeah, 0.02 or 0.02 is equal to, what kind of confidence level did we want? 95% confident. So that means our Z star is what? 1.96. So 1.96, and then square root. What are we putting in for P hat? 0.5. We're using our conservative estimate. So I've got 0.5, and then 1 minus P would also be 0.5 over N. So first thing I'm going to do is divide both sides by the 1.96. Yep. It said using a conservative estimate.
So will it tell us when we do that?
When you don't know it, or when it says use a conservative estimate, we're going to use P hat of 0.5. Yes. So the reason that we're not using the 0.813 is because that's not something that we got from a sample. That is to pass the validity test. Like, that's the benchmark that has to be reached in order for the validity test to be passed. Yes?
So even if we're using a conservative estimate, we don't have to do 1 minus P hat?
So 1 minus P hat, though, that if P hat is 0.5, what's 1 minus 0.5?
It's just 1.
Yes. So that's why it's 0.5, 0.5. All right. So I divide both sides by 1.96. Do not put that in your calculator yet, because we don't want any decimals here that run off the screen. We want to be as precise as possible for as long as possible. So then I have my square root of 0.5 times 0.5 over n. 0.5 times 0.5 is what? 0.25, so I'm just going to replace that with 0.25. That one doesn't run off my screen, so I'm good. How do we get rid of the square root? Square both sides. So squared and square root cancel. So again, I'm not typing this in my calculator yet. I have 0.25 over n. How do we get n on a side by itself? We're going to times it. That'll move it to the other side, but then I want to get rid of that fraction that's over there on the other side, so I'm going to have to divide by that. So my left-hand side and my n are basically just going to swap places. Then I can type it into my calculator. So I would have n equals 0.25 divided by, parentheses, 0.02 over 1.96, close my parentheses, and square it. What'd you get? 2,401. I kind of like this example and I kind of don't, because this one did come out to be exact, right? At least when I typed it in on my calculator, it was exact. Most of the time, when you divide by this fraction squared that already has a bunch of decimals in it, you're not going to get a whole number back.
Oh, I'm rounding it up.
You rounded yours up?
Yeah, but it was 0.9995.
My calculator just automatically rounded that one up. But remember, if it has any decimals at all, if it had come out to be 2401.000001, we would round it up to 2402. In the activist group's previous petition, 85% of the signatures were valid. Using this value as a guess for p hat, find the sample size needed for a margin of error of at most 2 percentage points with 95% confidence. So I want you to basically do what we did in question number 1, but now you're going to use a different p hat value. We're not doing a conservative estimate. We're using the 85% that they got last time. So try this whole thing again. Find the n value.
Show all the work if you just go from this to this and continue.
I'm fine if you go from this to this. Because I can, like, I know that that has to be that times that. I know where that's coming from because you set it up. I see your critical value there, and you're squaring it to get rid of the square root. That is totally fine. Yes. We can finish up our calculations in about 1 more minute for the people that are still working on it. It's only squaring the 0.85. I believe you. All right, try that. Oh, what is it doing? Okay, so what we're going to do instead 0.85 divided by 1.96. We're going to square that answer. We're going to do, is it 0.1275 divided by, and then I'm going to use the answer button on the calculator. Why? Okay, something must be wrong here then. Okay, that's right. That, your margin of error is 85%. What do you want your margin of error to be? There you go. What do we get? 1,225, absolutely. Let's walk through this a step at a time. So you're going to have 0.02, that's your margin of error, that didn't change. 1.96, critical value stayed the same. P hat and 1 minus P hat are now 0.85 and 0.15. So we divide both sides by the 1.96. I multiplied my decimals together up on top. We're going to square both sides. And then swap it around. So n equals 0.1275 over 0.02 divided by 1.96 squared. I got 1224.51, round up. That sample is a lot smaller than what we got in number 1. What was number 1 again? 2,401, so almost half. It's not quite half, but ballpark half-ish of what we needed before. What if the company president demanded a 99% confidence instead of 95% confidence? Would that require a smaller or a larger sample size, assuming everything else remains the same? So no more than a 2% margin of error. Larger sample size. To be more confident, they have to check more signatures. Yes? Could you solve for it? You could solve for it if you want to, but you still need to answer the question, which is, would you require a larger or smaller sample size? So if you went through and you calculated it with a 99% confidence in that critical value instead, that would be fine. You would have a more precise answer, but then you would still need to say that we need more signatures. So. Fantastic. All right, now we've done the 4-step process. We will continue to do the 4-step process in every chapter from here on out. The tests that we run, the name of the procedure is going to change. The specific formulas that we're using are going to change depending on what test we're using, but this 4-step process stays the same. State, plan, do, conclude. All right? Does everybody feel like they know how to at least begin the homework?